Hey guys, in this video I'm going to try to implement Dropout as Bayesian Approximation, which is a technique that comes from University of Cambridge, and it has to do with the idea of capturing the uncertainty in your model using Dropout. So their particular idea is that you can view Dropout as a kind of variational approximation, and you can very easily generate samples from that variational approximation, which you can then use as an approximation to your true posterior. And so because of that, you're able to obtain the posterior mean prediction, the posterior variance prediction in a regression problem as an example, and that can be useful. So what I'm going to do is implement this in TensorFlow, and I hope that you will enjoy it. I'm going to try to do it all in one go, so you'll get to see all of the mistakes that I make. So I've already gone over here and imported NumPy and TensorFlow. What I'm going to do is define a class, and we'll call that variational dense. I'm going to borrow some of the sort of syntax from Keras, although I'm not going to use Keras. So we'll call this the variational dense layer class. And what does it need to take as an input in its constructor? So if I go back over here, if this is a single layer, then for I ranges over 1 to the number of layers in the network. So each layer has an associated dropout probability, or I suppose it might be easier to think of it as the keep probability. So this is the probability that you don't drop something out. So we'll call that model prob. So one of the things we need. I'm going to need to know the number of inputs and the number of outputs of the hidden layer. And I need to know actually maybe I'm going to reorder this slightly. So we'll have model prob, and then I need to know this quantity called lambda, which I'll just write as L for the moment. L is, I think, a abbreviation for what all of this stuff is going to be wrapped into. So you see each in these regularization terms down here, they have L squared divided by 2 times tau times the number of samples. What I'm going to do is wrap up L squared, 2, and tau into one variable and call it lambda. And actually I suppose you don't even need tau in there necessarily, because you can multiply this whole objective through by tau and you'll still find the same, you'll still preserve proportionality. So I guess it's really just L squared and 2 that I'm rolling into a thing called lambda, and we can just forget about tau actually for the purposes of obtaining the matrices that fit the objective. So the idea here is that we are going to learn a matrix M where if you're dropping out the columns of the matrix to obtain a new matrix W, then your set of W's, which you can regard as a sample from your variational approximating distribution, they're still good for prediction. So that's kind of the idea behind this paper. So in order to do that, we first of all are going to, let's say, we need a Bernoulli distribution, so I'll call that model Bern. And then I'm going to import the Bernoulli distribution from the TensorFlow contrib distributions Bernoulli. Now the thing about the Bernoulli class, which can really get you, is that it actually takes a default first parameter of the logits, which if you're putting in a probability, is not going to give you the correct answer. So you need to make sure to specify the keyword probs and not just leave an empty first input if in fact you're dealing with probabilities and not logits. Model prob. Now the other thing I can do is make sure the D type is correct. We're going to be using float 32s for this. It's not going to be int32, which is the default, because it'll cause a type error. And we also need to define, if this is an individual layer, we need a model M. So M is going to correspond to this matrix that is being learned. Okay, this is what is going to be dropped out. And so we'll call that tf.variable, and then we do tf.truncated to normal. And then the shape is going to be n in, n out. The standard deviation, I'm going to make it pretty small. And then I think the other default parameters are okay. And we'll do self.model little m. Model little m is like the bias. And that is denoted down here by a little m. Okay? So we'll just initialize that to be zeros. So we'll do tf.zeros, and then the size of it needs to be the number of outputs. All right, so from here, what we need to do is actually define a sample from this layer, which will correspond to this kind of dropout mechanism. Now, in this example, it's kind of flipped. M is transposed to how I'm going to use it. So I'm actually going to do diag dot m rather than m dot diag. So tf dot matmul self dot burn, excuse me, model burn dot sample, and then how many do I need? I need n in of them, and I need to do tf.diag to make it the dimensions match. And then I need to do model m over here, and this will give me a kind of dropped out version of m. I'm missing a parenthesis. Okay, good. So from here, I'm going to also implement a call method. It'll take in self, it'll take in some input x, and then I'll add an activation function, which I'll just make by default the identity function. And then, let's see, we're going to do output equals activation tf.matmul x self.model w plus self.model m. So what I've done is I've applied the activation to, you know, the inputs matrix multiplied with the stochastic matrix w, and then I've added in the bias. By the way, you'll notice I'm not doing anything random with the bias. The paper suggests to use a point estimate of the bias. So that's what we're going to do here. By the way, I'm also going to check if self.model m.shape1 equals 1. So if we're doing a regression problem, I'm going to squeeze this to make sure that it's just like a vector and not some matrix, so that it has rank 1 rather than rank 2. Just a preference. And then at the end we can return the output. Alright, so now maybe we can start generating some data and visualizing it. So I'll import pyplot. All right, so now let's do x equals np.random.normal, and then we'll do size equals n samples equals, let's just do 10 samples. And I'll do y equals np.random.normal how about 5 times np.cosine 5 times x divided by x np.abs x plus 1. I just made that up. I don't know if you could tell or not that I did. All right, good. Let's visualize this. blt.figure, big size equals, let's make it a nice big figure, 17 by 7. blt.plot. I'm going to ravel this so it's a vector. We'll do x. Oh, you know what else I'm going to do? Is I'm actually going to make an xpred, which will be np.linspace. I'll go from -3 to 3, num equals 100. And I'll do np.atleast 2d to make sure it's a matrix. I'm also going to add some more features. So I'm going to say x equals np.hstack x squared, and x cubed. Same thing with xpred. I'm going to hstack some stuff just to make it a little bit more interesting than predicting just as a function of one variable. I think this makes it more interesting. X, and then I'm just going to plot with respect to the first component versus y. Grid, plt.show. All right, let's take a look. Let's see if this runs. Good to make sure that it runs. Indent, identity. Whoops. It's kind of hard to look at. Let's make these red dots. I admit it's kind of hard to see what the pattern might be in that data set. Let's try this. Okay, that's a bit better. A bit easier to see what the pattern is. Okay, so now I might also add a property to this class, which will be the regularization. So in the paper, there's a special regularization, or rather there's a special objective function that they're using. So they basically have this log likelihood, okay, ignoring tau for the moment because you can multiply this whole thing through by tau and nothing really changes. But anyway, they've got a negative log likelihood, and then they also have a sum of squared L2 regularization, which has a particular strength associated with it, given by the product, in the case of the matrix, by the keep probability for dropout, and also the lambda quantity, which is L squared over 2. And so I guess what I will compute is lam. I need to save self.lam equals lam. And then I'll do return lam times and then it's going to be self.model prob times tf.reduce sum, tf.square self.model m plus tf.reduce sum tf.square self.model little m. And that should give us the regularization term for this particular layer in the neural network. All right, so we have created sample data. Now we will create the TensorFlow model. All right, so what do we need? We need a model x equals tf.placeholder, tf.float 32 as usual, and then the shape will be none by n feats, where n feats equals x.shape1, in this case 3. We need a model y, which will just be another placeholder. But it will just have shape none. Okay, so what do we need now? Let's define the number of hidden layers. N hidden, let's just say that's 100. I think that'll be okay. So now I can start making my layers in the model. So I'll call it variational dense, and it will take in how many features come in, n feats come in, how many features come out, n hidden come out. What should the model probability, model prob be? It should be 0.9, okay, not too low. Model prob, and lambda, model lam, will be I'll just have my naming be consistent here. Model lam will be 1e minus 2. I just made these numbers up. One could potentially do Bayesian optimization to make sure they choose the right value. All right, let's say that we have a few of these things. So again, how many features come in and hidden come in? How many features come out and hidden come out? How many features come in and hidden come in? How many features come out? One comes out, because this is in fact the model prediction. All right. So here I might define the model sum squared error, which is, in this case, it's basically the negative log likelihood for the regression case. So tf.reduce sum, tf.square, and then model y minus model pred. And then we'll do model loss equals oh, you know what? I've actually I've forgotten to do something. I forgot to call all these things. So we'll call this model out 1 equals model L1. I'm going to call it on model X, and we'll do tf.nn.relu. We'll use relu activations, and then we'll do model out 2 equals model L2. What goes in? Model out 1 goes in, tf.nn.relu, and then we have model pred. And we just feed in the identity. Okay, now I think it's okay. The model loss is going to be the model sum squared error plus regularization. So this is negative log likelihood plus regularization. So we'll have model L1 dot regularization plus two. All right. So then we might have a train step equals tf dot train dot let's do atom optimizer 20 minus 3. We'll just leave everything else the same. Dot minimize. What do we minimize? The model loss. Okay. Maybe I'll make a model mean squared error, which will be model SSE divided by n samples. And then we'll do with tf.session as sesh sesh.run tf.global variables initializer for I in range 1000 sesh.run train step. What do we need? Model x maps to x, model y maps to y, and then we'll do if I mod 100 equals 0. We'll print out iteration I mean squared error format sesh.run. This will just be the train set mean squared error. All right, well, now it's now that I've done that, let's see how it will or will not run. Wow, it ran. That's cool. All right, so now let's choose the sample from the posterior. N post equals 1000. Y post equals np.zeros. xpred.shape 0 by n. Actually, let's do n post by xpred.shape 0 for I in range n post. Y post I equals sesh.run model pred model x maps to xpred. And then down here we'll do for I in range and post ELT.plot xpred, just the first dimension, y post, get the appropriate sample, plot blue lines, and we'll make them somewhat transparent. Okay, and now we can run it again. So I think that looks pretty good. I think that looks pretty good. So the idea here is, let me make the figure a little bit smaller. I think I made it too big. Make it 8 by 6 or something. We'll just run it again. It's pretty fast too. I'm pretty happy with that. So I think the idea here is that you can look at these uncertainties. So, if you condition on any particular input, then you're going to be able to characterize both what is the mean and what is the variance of that output. So you can tell where you're quite uncertain. For example, if you're predicting way out here, you're going to see quite high variance. You're going to be relatively uncertain. But somewhere here, you have a lot of agreement between your samples from the approximate posterior. So you have higher confidence. I think you could see it better in the last one. Let me see, does this stretch at all? It does. You can detect a slight bit of multimodality going on here. Let me try it with fewer samples and see if we can get some more obvious multimodal behavior going on. It might also help to run it for more iterations. So again, you do see some multiple modes in the output, which I think might actually be my favorite part of this method, is the fact that you can see different interpretations of the data coming out in the regression output. So anyway, that is the technique as best as I understand it from this paper. Again, it's called Dropout as Bayesian Approximation, representing model uncertainty in deep learning. Cool paper. I really recommend it, and it is very simple to implement. And you've seen some code now on how to do it in TensorFlow, and I hope you enjoyed this video. So thank you so much for watching, and be sure to like, comment, and subscribe if you like this video and want to see more. And I will see you guys in the next video. Bye.